Jupiter, the colossal king of our solar system, cloaked in swirling storms, has always captivated humanity. But how truly complex is the journey to this majestic gas giant? I'm Dr. Sachi Vale, your science communicator at Science Aura. Today, we're delving into the intricate dance of celestial mechanics and engineering marvels required to reach Jupiter. It's not merely about distance, it's about velocity, trajectory, and the sheer energy needed to escape Earth's gravity and then accelerate across millions of kilometers. The journey's duration is highly variable, influenced by rocket power, spacecraft mass, and the mission's objective, a flyby or orbital insertion. To understand the challenge, we first grasp the scale. Jupiter is about 778 million kilometers from the Sun, roughly 5 times Earth's distance. This enormous separation means traditional chemical rockets, while powerful, face fundamental limitations in terms of fuel and speed. Consider the tyranny of the rocket equation. Every extra kilogram of payload requires exponentially more fuel, making human missions incredibly difficult. Then there's the home and transfer orbit, the most fuel-efficient way to travel between planets. It's a slow elliptical path, dictating long travel times. For unmanned probes, these journeys typically span hundreds to thousands of days, often leveraging gravity assist from other planets to gain speed. But what exactly is a gravity assist, and how does it shave years off a deep space journey? It's a cosmic billiard shot. The Pioneer 10 and 11 probes were our first emissaries to Jupiter. Pioneer 10, launched in 1972, reached Jupiter in just 640 days. It was a flyby mission, meaning it didn't slow down to orbit, but instead used Jupiter's gravity to accelerate out of the solar system. Then came the Voyagers. Voyager 1, launched in 1977, took 546 days to reach Jupiter, using a gravity assist from the gas giant itself. Voyager 2 followed a slightly different path, taking 690 days to reach Jupiter, also on a flyby trajectory towards Saturn and beyond. These flybys were critical for initial reconnaissance, giving us our first close-up look at Jupiter and its moon. But to truly study Jupiter, we needed to orbit it. This requires a far more significant deceleration, a braking burn upon arrival. The Galileo probe, launched in 1989, was our first dedicated Jupiter orbiter. It took 6 years, or 2,242 days, to reach its destination. Galileo used multiple gravity assists, Venus, Earth, and then another Earth flyby to gain enough speed. A truly complex trajectory. Its mission provided unprecedented data about Jupiter's atmosphere, its magnetic field, and its fascinating Galilean moons. More recently, the Juno spacecraft, launched in 2011, took 5 years, or 1,811 days, to reach Jupiter, employing an Earth gravity assist. Juno's polar orbit allows it to peer beneath Jupiter's dense cloud tops, revealing secrets of its deep atmosphere and core. These unmanned missions showcase the power of clever orbital mechanics and robust engineering, making long journeys feasible. But for human missions, the challenges multiply exponentially. We're not just sending instruments, we're sending lives. The weight of life support systems, radiation shielding, and return fuel adds immense mass, increasing travel time and current chemical propulsion simply isn't efficient enough for rapid human transit to Jupiter. It's a fundamental hurdle. Imagine a human crew enduring several years in deep space. The psychological toll, the physical degradation from microgravity, and cosmic radiation are immense concerns. Radiation, especially from solar flares and galactic cosmic rays, poses a severe health risk. Jupiter itself has an intense radiation belt. To make human journeys viable, we need to drastically reduce travel times, ideally from years to mere weeks. This demands a paradigm shift in propulsion technology, moving beyond the chemical rockets that have served us so well. So what are these revolutionary propulsion concepts that could unlock rapid interplanet? One of the most promising avenues is nuclear propulsion, specifically nuclear thermal propulsion, or NTP. Instead of burning fuel, an NTP engine uses a nuclear reactor to superheat a propellant, typically hydrogen, to extreme temperatures. This heated gas is then expelled through a nozzle, generating much higher thrust and efficiency compared to chemical rockets. NTP could slash travel times to Jupiter by half, bringing a human mission down to perhaps 2 years, a significant improvement. Another concept is nuclear electric propulsion, or NEP. Here, a reactor generates electricity to power ion thrusters. Ion thrusters provide very low thrust, but are incredibly fuel efficient, offering continuous acceleration over long periods. While slower to accelerate than NTP, NEP could eventually achieve higher velocities, potentially shortening total travel time for long missions. Pushing the boundaries further, we consider fusion propulsion, harnessing the power of the stars for interstellar travel. If perfected, fusion rockets could offer even greater efficiency and thrust than fission-based nuclear systems. However, controlled nuclear fusion for power generation is still a major scientific challenge, let alone for propulsion. Then there's the truly futuristic antimatter propulsion. This is where matter and antimatter annihilate, converting mass directly into energy. The energy yield is enormous, offering the theoretical potential for incredibly fast travel, possibly weeks to Jupiter. But the challenges are monumental. Creating and storing antimatter in sufficient quantities is currently beyond our technological grasp. Even generating a tiny amount requires vast energy, making it an incredibly distant yet tantalizing prospect. Beyond rockets, exotic concepts like solar sails, which use light pressure for propulsion, are also being explored. While offering continuous fuel-free acceleration, solar sails are very slow and primarily suited for cargo or long-duration science missions. Then there are concepts like plasma rockets, which use electromagnetic fields to accelerate a superheated gas. These offer higher specific impulse than chemical rockets, making them more fuel efficient for future long-haul journeys. The journey to Jupiter is a grand challenge, pushing the very limits of our understanding. It requires not just bigger rockets, but fundamentally different ways to move through the cosmos. Each mission, from Pioneer to Juno, has chipped away at the unknown, providing invaluable data and refining our techniques. These unmanned probes paved the way, demonstrating the feasibility of interplanetary travel, albeit over long durations. But the dream of sending humans to Jupiter, even if only for a flyby, remains a distant goal, demanding incredible technological. The development of nuclear-based propulsion is likely the next crucial step to significantly reduce travel times. These technologies promise to transform our solar system from a vast expanse into a more accessible neighborhood. Imagine a future where a journey to Jupiter could be measured in months, not years, opening up unprecedented opportunities for exploration. Such missions would allow us to study Jupiter's moons, particularly Europa and Ganymede, for signs of. The scientific return would be immense, deepening our understanding of planetary formation and the conditions for life. Yet, even with advanced propulsion, other challenges remain: radiation shielding, life support, and long-term psychological health. The journey to Jupiter is not just a mechanical problem, it's a holistic human endurance test. Each step closer to Jupiter is a testament to human ingenuity and our insatiable drive to explore the unknown. From the first rudimentary rockets to the dreams of antimatter drives, our ambition grows with our knowledge. The complexities of reaching Jupiter are immense, a true grand challenge of celestial mechanics and technological innovation. But it's a challenge humanity is uniquely equipped to tackle, driven by curiosity and the pursuit of knowledge. The journey to the gas giant remains a beacon, guiding our scientific progress and inspiring generations. As we gaze upon Jupiter, we're reminded that the greatest adventures often lie beyond our current reach, waiting for our ingenuity to catch up. Thank you for joining me on Science Aura as we explored the incredible complexities of reaching Jupiter. Stay curious and keep looking up. The sheer amount of thrust needed to accelerate a human-rated vessel to high speeds and then decelerate it at Jupiter is staggering. Chemical rockets are simply too inefficient, demanding unrealistic fuel loads for rapid human. We need propulsion systems that offer far greater specific impulse. How much thrust per unit of propellant? Nuclear thermal propulsion promises a specific impulse twice that of the best. This translates directly into less fuel mass required, making larger payloads and faster trips possible. Nuclear electric propulsion, with its ion thrusters, offers even higher specific impulse, but at a much lower thrust level. Think of it as a marathon runner versus a sprinter. Ion thrusters are the marathon runners of space travel. Antimatter propulsion, if realized, represents the ultimate in specific impulse, approaching the speed of light itself. This would transform interplanetary travel into something akin to intercontinental flights, dramatically shrinking our solar system. The pursuit of Jupiter travel forces us to innovate, to break scientific barriers, and to dream. It's a journey that began with unmanned eyes, and one day will hopefully include humans. The road to Jupiter is long and challenging, but the rewards of discovery are immeasurable. It's a testament to the enduring human spirit, forever reaching for the stars. From Science Aura, I'm Dr. Sachi Vale.